So today is the last of the SAFL Spring Seminar Series. And so I'm very excited to have this exciting seminar to conclude this seminar series. Yeah. Also, I want to take this opportunity to thank our seminar committees for their excellent job for this. So let me say a few words about Nels Nelson. He was a SAFL alumni. He did his graduate school here, study here, and then afterwards, Mr. Nelson went to bar engineering and to head for his long career of 30 years there. So he became a leader in engineering, research, and a lot of other things. So he was a leader in the community. And then after he passed away, then his friends, former colleagues, and many other people who knew his work established this Memorial Fellowship. And this fellowship is for a graduate student doing research at SAFL in the area of water resources. And this year, we have our student winner, Noah Gallagher. And next, I'm going to invite Noah's advisor, Professor John Gallagher, to introduce Noah.
Thank you, Leon. Noah is finishing his master's degree, and he will soon enter the PhD program. Andy Erickson and I are his advisors. We are co-advisors, and we are impressed by his abilities and his maturity as a graduate student. He started with us as an undergraduate, and we immediately put him in the field, sampling stormwater ponds, going out and measuring infiltration rates, that sort of thing. He came back in the lab, was working in the analytical chemistry laboratory, analyzing what he'd done in the field. And then for his master's thesis, he said, I want to do something computational. So he didn't use any of his undergraduate work at all. He's now doing computational work. His thesis will be, you're probably going to hear part of this today, but I don't think he's going to cover this topic. He wants to combine, part of his thesis will be to combine the stormwater management model and GIS programming to make a tool that you can use with both of these programs together. And that would be a powerful tool. So hopefully it'll work out well. He's going to work with, I think, the EPA in developing this program. So Noah, by the time he graduates, will have done field work, will have done laboratory chemistry work, will have done computational work. He'll be pretty well-rounded. And he'll be ready to go into the area of engineering. So I would like to congratulate you, Noah, on the Nels Nelson, winning the Nels Nelson Award, and it is well deserved.
Thank you, John, and thank you to the SAFL committee, as well as Nels Nelson's family and Bar Engineering for setting up the fellowship. It's really appreciated to continue the work of water resources and investing in the next generation here at the U, so it is very much so appreciated. So my title of the presentation today is Adapting Stormwater Infrastructure in the Face of Climate Change. A couple of additional acknowledgements. The funding for part of this project was provided by the Local Road Research Board as well as MnDOT. And I want to say thank you to the MnDOT team that we've liaisoned with, Eric Brenna and Jackie Duran, as well as the technical advisory panel that has advised us throughout this project, and the wonderful researchers here at SAFL and other parts of the university that have mentored me and been wonderful resources and colleagues on this research. So, the topic of this presentation primarily deals with extreme rainfall events. The first thing that you need to understand is that these can be very dangerous. They're distinct from river flooding in the event that they can cause flash flooding, which is due to precipitation causing runoff, which can end up in places far, far from rivers, but still be very destructive. They can also be immensely expensive. In 2012, Duluth saw record-breaking rains of up to 10 inches, and it was a very, very expensive storm. That photo shows some of the flooding, and estimates put the damage at over $100 million. The other thing you need to understand about extreme storm events is, unfortunately, they appear to be increasing. The first place we see this is in the rainfall frequency estimates. The first real robust set was put out in 1961 called TP40, and since then they were updated by NOAA in 2012 with the Atlas 14 estimates. From there, the 100-year 24-hour storm increased between 19 and 28% in the 3 regions we studied in Minnesota. These are significant increases and show a lot more water as a possibility to happen during a precipitation event. Additionally, climate change is happening. Part of the research team looked at 34 different global climate models and put them on the rough track that can really span the gamut as to what the climate can do over the next several decades. And they did this on a downscaled system. It was wonderful work done by Bruce Wilson and Dr. Bill Erb. The plot here demonstrates that there are additional increases over Atlas 14, particularly these large rainfall events. All of them show that the 75th percentile and the median are increasing over Atlas 14. So not only have they increased over TP40, but they're even getting larger. And this is a problem because a lot of our infrastructure was either not based on TP40, based on TP40, and so it might be undersized for these rainfall events. In order to study this, the methods we used involved 3 study watersheds, one in Duluth, one in Minneapolis, and one in Rochester. We used EPA SWIM, which is an open source watershed modeling software, and ran a variety of storms from both the TP40, Atlas 14, and these new GCM estimates. And we looked at several scenarios. The first, a baseline where we would do nothing. Next, adding a large amount of rain gardens and biofiltration to the watershed. Next, upsizing the pipes in the watershed by about 30%. Next, adding more stormwater ponds to the watershed. This would be so that the additional volume brings the total capacity of the watershed up to the volume of the 2-year storm. So if you had a storm that occurs only once every 2 years, in theory, these stormwater ponds would be able to contain all of it. Next, we looked at smart stormwater ponds, or retrofitting existing stormwater ponds with smart actuators that are connected to the cloud and can draw down water within the pond before a storm event, giving you additional storage without having to build a new pond. And finally, we looked at new smart ponds. In addition to building new ones, we would make them smart, which would provide additional capacity. Now we got to talk about some of the results. I'm only going to be focusing on the Kings Run watershed because there's a lot of data and we only have so much time. So we're going to be looking at this particular node, SP113, which is a stormwater pond next to a residential area. These are multi-family residential units and vulnerable to large precipitation events. Here are some of the results. The different adaptation strategies are color-coded here, and I'm only displaying the 2, the 10, and the 100-year event. We do have numbers for the other ones, but these were the ones that show some interesting trends. That black dotted line is the level at which that stormwater pond begins to overtop and induce flooding in the surrounding area. So that's the no-no zone. We don't want to go above that line. A couple of things to note is that there is a clear increase from the TP40 estimates to the climate change adapted estimates for that baseline number. It shows that we might not have experienced flooding in a 10-year event, but now with this increase in storm size attributable to climate change, there is going to be potential overtopping of that stormwater pond at the 10-year event level. So that increase is noticeable. Another important part of this is that there are 2 strategies that seem to stand out from the rest in terms of their performance. The first is extra ponds, which provides considerable benefit across pretty much all of the storms, though as we increase storm size, the effect seems to get smaller. And then the winner, if you had to call it that, or the one that provided the most benefit, would be smart storm ponds that provide about 50% more benefit than the other ponds alone. For the most part, the other strategies don't seem to have a lot of effect on this particular node. Particularly pipe upsizing, which actually increases the flooding for the large return interval events, because this is a downstream node and larger pipe just means that the water gets there faster. For some of the upstream nodes, we actually saw substantial reductions, but on a watershed scale, pipe upsizing does seem to have this effect the further down you go in the watershed. Additionally, we looked at flow rate at the outlet of the watershed, and we saw similar trends, where there is an increase as you go from TP40 to Atlas 14 to our climate predictions. And there again are two standout adaptation strategies, smart ponds and, more ponds and more smart ponds, with the more smart pond option performing slightly better than the extra pond scenario. And the performance difference between baseline and the adaptation scenarios getting smaller and smaller the higher or the larger return interval event that you look at. So the brief summary of the results is that new rain gardens seem to have little impact on flooding in pretty much any of the watersheds except for the 2-year event. They just get overwhelmed with the amount of water. If you're infiltrating at a slow rate and the rate that the water's coming down is greater than that, it's almost like they aren't doing a ton. Additionally, pipe upsizing, good for upstream, not so good for the downstream nodes. Additional stormwater ponds, again, had that large impact, and it started to get less effective after 100 years, where smart stormwater ponds had some small marginal impact, but it was still a larger impact than rain gardens in Rochester. And the new smart stormwater ponds were the most effective, even if they did have a decrease in efficacy for the really large events. Next, we looked at the cost of these adaptations, because it doesn't matter if we know what we can do if we can't afford to implement these in the watersheds that we're trying to protect. We used the community-enabled lifecycle analysis of stormwater infrastructure costs, also known as CLASSIC, which was developed by Colorado State University and the Water Research Foundation. And it looks at installation and maintenance costs over 20 years. We also sourced some outside data from the city of Minneapolis, as well as some private companies, to get a good estimate on what smart pond adaptation or pipe upsizing adaptations would cost in the real world. And the differences are a little bit more staggering than the adaptation benefits. There's always going to be a cost to just maintain the watershed. Ponds are expensive to dredge up and make sure that they maintain their capacity as they fill up over the years. But compared to some of the very expensive options like pipe upsizing, it's not a ton. One really beneficial thing was that the extra pond scenario seemed to fall in the middle of the range as far as costs, and it was one of the most effective options. However, this does not consider land costs. So you would have to purchase new land, which can be extremely expensive, particularly for urban watersheds like Minneapolis. Regardless, it does seem like this sort of resilience is going to be expensive, but that has to be balanced against the fact that when we don't act, you can have events like the Duluth flood, which causes damage to property and oftentimes threats to individuals' well-being. A couple of other points that had to work out over this process is water where it normally isn't. This is a photo of a flooded international airport, Fort Lauderdale, that happened just this past month. And water typically doesn't end up on a tarmac. So when we use existing models outside of their calibrated range and are throwing these 500-year climate-driven events at them, they sort of fill up with water and act in ways that the initial modelers might not have expected, because these are new storms that we're just understanding to be that large. So water can end up in unexpected places, and the overland flow of that water becomes very important to that model's overall functioning. The solution that John briefly mentioned in his introduction is LiDAR-derived storage curves and drainage areas, using some aerial LiDAR data in order to develop a topographic understanding of the watershed. We can do a lot of really fun things, like put water in that upper pond and watch it drain into the lower pond with some computer modeling. This would improve accuracy for extreme events where these connections might not be apparent for smaller rains, but they do become real conduits of water in the large events. And so this also lets us translate model results to flood maps because we're better able to understand what a flood volume in a particular area looks like when you spread it out across the landscape. So it can give better reflections of what might be at risk during these large storm events. So what I'll be working on going forward is developing that GIS-based tool to automatically assist modelers in sort of defining these edge cases where there's really a lot of water in the system. It creates storage curves, finds and characterizes possible overland flow paths in order to improve those models. And additionally, try and predict what is enough for a watershed. We need to be looking at the adaptations and what is feasible from a budgetary perspective, as well as effective at actually protecting the watershed itself. So thank you all, and thank you to Bar Engineering and the Nels Nelson family again.
Great. Now the floor is open for a few quick questions. Chatting.
Thanks, Noah. Really interesting work. I have a question about deliverable to MnDOT in the end. So you're looking at different solutions. It seems like they're applied like one solution for the entire watershed, or are you also looking at different combinations? So maybe in the upstream area, we apply pipe sizing, but downstream we add more ponds or something like that.
So we looked at the adaptations in isolation across the entire watershed to sort of get that pro-con list of what are particular adaptations effective at, but we don't get to make those decisions for watershed managers. They might take into account some of this cost data, as well as the summary of what is good at reducing flooding effect, and make those combinations together. One thing to say is that they are occasionally competitive with one another. If you turn some area into a rain garden, you can't turn that same area into a pond or a smart pond. So there are some trade-offs in terms of them being mutually exclusive. Long way to say, no, we didn't combine any of the results, but we hope that our insights would allow stormwater managers to do so responsibly.
So this is an expert from Bar Engineering as well as from our faculty.
Thank you. This is very interesting, and also congratulations. I have a question with respect to your data that you already have it on your screen. When you compare TP40, which was published 1961, and Atlas 14, which came just in the past 10 years, probably even less than that. You look at the 2-year events, they're comparable. You get to the 10-year events, there is some differences, is small, but when you get to the 100-year event, then the difference is large. Do you know why?
I will say no, but my educated guess, based on what I understand about the Atlas 14 methodology, is that they just simply had more data. That there were more larger storms on record. So these very large events, when they were looking at the meteorological record in 1961, didn't necessarily include as many large events. So when they were included in the Atlas 14 calculations, it does increase just that sort of large event end of the estimates. Though don't quote me on that.
No, I mean, you said, I think you're right in a sense that if your record is short, the chance that the 2-year event is not going to change is very high, that it's not going to change. And 10-year might change a little bit, but it's even if they didn't have larger storms, I suspect still you would get a very different result with the 100-year. Oh, but thank you.
Thank you. Well, next, I would like to invite Professor Gallagher to come and to present the award to Noah. And we need a few pictures. Next, we are going to have the second part of the program. And as a tradition of SAFL award ceremony, we always invite a distinguished researcher from outside to come to give a keynote talk about research. Okay. And today, I'm very excited to introduce Dr. Peter Sullivan from NCAR. And Dr. Sullivan, he is a leading authority in the large eddy simulation study of atmosphere turbulence, ocean turbulence, their interactions, and a lot of other processes in the geophysical area. Dr. Sullivan, he earned his degree, bachelor and PhD degree in civil engineering. And in between, there's a master's degree in mechanical engineering. And after his PhD, he went to work for Boeing as an aerospace engineer for a number of years. And then afterwards, he went to NCAR to study geophysical environmental flows. Yeah. So have you noticed that actually I have just covered the 4 affiliated departments, so area affiliated with the SAFL. Software engineering, mechanical engineering, aerospace engineering, and earth science. Yeah, okay. So Dr. Sullivan, okay, he really did a lot of wonderful pioneering work using high-fidelity computer simulations to look at atmospheric and develop earlier models and associated with land, associated with ocean waves, and he was among the very first few did that. And also he used the simulations to study turbulent flows in the ocean and their interactions. And also, Dr. Sullivan, he has helped many students and young scientists. And at first I got to know him, that was, well, when I was still a graduate student, and Dr. Sullivan organized a workshop at NCAR. And my advisor, Professor Dick Yu, was invited to give a talk there. And then my advisor got busy with other things, so he sent me to go to that. I thought that was just a regular meeting to give a talk. And it turned out that was a workshop, and all the other speakers were well established big shots. And then I was just a student among them, and Dr. Sullivan, he took care of me very well. Yeah. And afterwards, there are many occasions, like, when I, moved on with my career, and then he helped me at every stage of my career. Yeah. And even just like several years ago, when we went together to a government lab in Monterey Bay, and then at that time, Dr. Sullivan actually gave ride to me every day in that week. And he taught me so many things, including English phrases. I was sitting on the passenger side, then he explained to me what a shotgun means from Western movies. Yeah, okay. And last night, after the dinner, he described to me, he said, well, the research we are doing is called outdoor fluid mechanics. Okay. Well, I like these words. Okay. So basically at the SAFL, we look at fluid flows happening in nature. So that is really outdoor fluid mechanics. Yeah. Okay. Well, without much ado, well, let me turn this podium to Dr. Sullivan, and let's, yeah, go to it.
Oh, Leanne's too kind. At that particular meeting that he recounted, he was the very first speaker on the agenda, and it went over really good. In fact, the Stanford people afterwards said, "Who is that guy?" And no, he was really good, and he's really excelled. It's really fun to watch his career just blossom over the years. Really good. So thanks for the invitation to come here. It's I forget what it's like to come to a university and feel the buzz of younger people trying all kinds of different things to find their way. It's really stimulating. Actually, for me, it's as much fun to come here and listen to them talk about their problems as it is for me to go home and sit in my cave. So that's really fun. Topic I'm going to talk about today, we're going to talk about marine boundary layers and the importance of ocean surface heterogeneity. I'll explain a little bit as that will go along, but they lead to secondary circulations, and we're going to do this with LES. Some of the sponsors of the work, my good friends at ONR, they have various programs over the years. And one of the things is they've been pretty free with the topics that I've wandered into. And so that's really appreciated. I have a contract with NOAA, and there was a really big experiment off the coast of Barbados 2 years ago. I work at NCART. We always advertise that it's funded by National Science Foundation, and that's really appreciated. Okay. Does it just work up, down, there? It should. Okay. Yeah, okay, there we go. It was just, okay. Oh. Okay. Some of the travelers along the way, Jim McWilliams at UCLA, do a lot of things with Jim. Ned Patton and Jeff Weil there at NCAR, and our good friend Joe Fernando at University of Notre Dame. I'm not really keen on outlines because I usually like to be surprised, but this one, I wanted to give you 2 points. What's out? I wanted to talk about many things, but there was just too many different topics, too short a time. So I'm not going to talk about steep waves. You have the expert with steep waves sitting over there anyways. We've done a lot of ocean boundary layer mechanics, especially with hooking Langmuir turbulence and density filaments. I was a little gun shy about that topic because I wasn't quite sure if the audience, if it was too far out there. It's pretty oceanographic. We've been doing LES of really stable boundary layers. And that's turned out to be really interesting. Johns Hopkins has a turbulence database. Okay, they've collected classic engineering boundary layer flows over time. They've put them on a web server at Hopkins. They've built really nice web interface tools, make it very easy for outside investigators who don't run simulations to get the data. So this is the first time we're actually going to add LES data to that database. So that's pretty fun. Not going to talk about, so what I am going to do, I'm going to talk about atmospheric boundary layers over SST gradients. I'll show that in a minute. That's pretty interesting. It's work that's been done in the last it is a pandemic work is really what it is. We're also going to talk about something that was kind of unexpected, atmospheric boundary layers over an ocean eddy. Okay. Maybe you've seen this slide before. It's really neat. John Woods Hole put this together. It shows all the various processes that go on at the air-sea interface. One of the things I really like, outdoor fluid mechanics, we have fluid mechanics in the air, we have fluid mechanics in the water, and there's this really interesting wavy interface that separates the two. So you got it. It's really fun. There are some reviews of different things if you wanted to look in the literature for different aspects of the problem. Okay, most of these are, I'll call them localized. Let's say a kilometer on the side, maybe, depending on which particular process you're looking at. Sea spray might be a really small box. Langmuir circulations could be in any kind of size box, wind stress, etc. And so that's a wealth of processes. But what we want to do is ask, well, that sits in the context of the real ocean. Well, there's a whole cascade, a whole plethora of different scales of motion. So I'd really like to be able, we're asking a question, okay, does that small scale stuff, is it okay if I wander around? Yeah, okay. Yeah, I like wandering around. All these processes live within the atmospheric boundary, live within the ocean, but right sits on top of it is something called submesoscale turbulence, okay? The oceanographers really like it. What happens is those submesoscale turbulence, they create gradients and currents and coupling. So do they leave an imprint on the atmosphere? That's kind of the question. It's just it's a garage question. We're going to go and ask, does it do anything? Well, here's kind of a really neat example of submesoscale turbulence. Those are plankton patterns in the Arabian Sea. And already the plankton are great tracers. And you can see, oh, there's a vortex, there's some filaments, really complicated fluid mechanics. Over here, you see some clouds. So you go, geez, are those two things connected? So that's kind of the theme of the story. Okay, so if you like this topic, if you're interested in submesoscale turbulence, Jim wrote a piece of poetry, I'll call it. It's a invited paper, and Jim backed off a little bit on the Greek symbols and told more about the story. So if you would, I gave this to a Russian friend of mine and he said, that's poetry. It's a really well-written article by Jim. It's really fun to read. So one of the things that Jim has, he talks about what happens in the ocean. There's planetary scale, skips down to the mesoscale, okay? So a long time ago, they thought the mesoscale was hooked straight to the microscale where dissipation happens, okay? Well, as time went along, they discovered that nature doesn't do that. It goes through this thing called submesoscale where it's a little bit of that, it's a little bit of that. And so really interesting regime. Okay, so so the point that it is, one of the things they discovered normally is that the atmosphere drives the ocean. That's the usual way that the climate people think about how circulations work on planet Earth. Well, what they've discovered is if you skip down a little bit, the ocean drives the atmosphere. It's reversed. Okay, they found this through satellite measurements, et cetera. There's correlations between wind speed and SST. Okay, it impacts important things in the atmosphere, divergence and curl and wind stress. They explored this regime using ROMS. It's like a mesoscale model for the ocean with NCAR's wharf sitting on top of it. Okay, so they found really interesting things, and that's what we'd like to look at a little bit. I know the topic of submeso might be a little bit unfamiliar, so I'm going to show you 5 pictures. I really like outdoor imagery. This is a really spectacular one. It's called Spirals on the Sea. So you can actually Google that if you were interested. Okay, so the neat story behind this is Scully Power was the first oceanographer to fly on a space mission. This is from the Apollo mission in 1980s, in the 60s or 70s, sometime like that. He looked out the window and that's what he saw. He took a whole bunch of pictures of it. Okay, wow. So fluid mechanics seems old, but that's relatively recent in fluid mechanics history. The radius of these things are about 5 kilometers. Okay, and they're tracing a really neat vortex street in the water. The next one, there's a bacteria bloom in the Baltic. Okay, one of the reasons it shows fantastic fluid tracer of fluid mechanics. It shows the scale the scale dependence of it. So you're looking at it, that's 10 kilometers down there. You see this rich structure. If you zoom in a little bit, okay, that's 1 kilometer. If you're sitting on a ship, you can see the problem. You see what you see right there, but you don't see all the background. That's what makes it hard. Okay. Oh, okay. So there's a satellite picture of SST along the Gulf Stream. See this really neat fingering right here? All these neat temperature jumps, really rich. Okay. This one over here takes a little bit of explaining. That's the Santa Barbara Channel off the coast of California. Okay, that's about 110 kilometers. The interesting thing is to look at these black long, skinny black lines. Okay, so it was taken with SAR. So SAR normally sees wind stress. It sees those small scale waves. Okay, so if you don't get a return, that means something damped the small scale waves. So those are surfactants that have converged into a single line, and they prevent the return to the satellite. So what happens is these lines are relatively long. Some of those might be indications of Langmuir circulations, but other ones are probably signatures of ocean frontogenesis. Frontogenesis, a really popular topic in oceanography right now, and really quite neat. So thing is, they're all over the place. It's very rich. Okay, submesoscale turbulence actually shows up in numerical models. If you have enough grid, takes enough grid to see that kind of stuff. So over there's pictures of the SST along the Gulf Stream. ROMS has the ability to do nested grids. So you zoom in like right here. Oh, you see a cold filament. Here's another cold filament. It ends up that when you look at the Greek symbols, cold filaments are more prevalent than warm filaments. Finally here, they can make vorticity. This is vorticity over normalized by Coriolis parameter. It's a submesoscale soup. You see vortices, fronts, filaments, all kinds of rich fluid mechanics at the top of the water. And finally, we get down to where I've messed around a little bit. This is actually a density filament that's undergone frontogenesis. You can see pale green water here, bright blue water there, scum lines in between. There's a shadow of a helicopter, so you kind of get a sense of the scale. We've hooked that mechanics together. This is a beautiful picture given to me by some friends at Scripps Institute. They were flying around. I was talking about Langmuir circulation. They said, oh, we see this all the time. So took that great picture. So we've connected what's over there on the left and what's over there on the right in a really big box. Okay, it's about 10 billion grid points to do that whole simulation. It's really interesting connection. Okay, so that's kind of what submesoscale turbulence looks like. No machine, no computer on the planet is powerful enough to do boundary layers and all those processes at the same time. So we're going to make the problem easier. We're just going to take a few peeks and look at some idealized simulations. Okay, so the first example, we're going to look at changes in what sea surface temperature does. Okay, so imagine you have an LAS box. This side of the water is from temperature theta. Over a little distance L, it jumps. We get theta plus delta theta. Okay, so we're going to blow the air across. This is what the isotherms are into the page. These are across front winds. Okay. It's interesting to take the case and actually take the geostrophic wind. We live on a rotating planet. Blow the winds into the page and ask the same kind of questions. So these are really big calculations. It's about 2.5 billion points in this box. Okay, so I put these little red things on there, partly for Leanne, in case he hasn't thought about it. We have periodic boundary conditions, okay, which means what comes out here goes in here, but we want to do a spatially evolving boundary layer. We don't want the debris from this side to spoil what comes in here, okay? So we've invented this, not invented, borrowed is very important in science. We call this fringe LES, there and there. I'll show you how it works in just a sec here. Okay, so imagine you have this really neat stratified wind tunnel. Okay, we're going to run LES in two boxes. One right here. If you just looked in that solution, you would be perfectly happy with what you got. Okay, in this bigger box, okay, we're going to put our SST jumps. Okay, but much like how a wind tunnel works, what comes out of here comes in here, but in a wind tunnel, the fan takes care of it, cleans up the flow, sends out nice clean turbulence on this side. So here's the blending function. So the equations slightly different than regular LES equations. We're going to add this forcing term right here. So essentially, it's the difference between what's in this box and this box. Okay, if we make this scaling parameter, this blending function big enough, what happens is it inherits all the properties of what's in the P domain. Works really slick. So you could do flow over waves. You want to do growing waves. There's an example of how you could do growing waves. Okay, so the key thing is these are parallel machines. We can run two LES simultaneously. If you're familiar with how MPI works, you can straightforward to do. Okay, let's look at just a little bit of example. Okay, so this is the warm side of the box. This is cold, all right? And so what we're looking at is vertical velocity, and it's a slice, an XY slice right through the box. And we're asking, how does the air change, or how long does it take for the air to change, get over here? So we're going from a convective state to a cold state. All right, so it's kind of fun. All right, so this is vertical velocity. Those things in the red are actually really well-known, well-studied convective structures in the atmosphere, convective rolls. So if you imagined they're turning like this in the atmosphere, different ones. Okay, so it's Coriolis, so it looks like it's moving up through the box. One of the important things to notice, look at how far it takes before this turns into stable turbulence. So you end up with this regime of very mixed up fluid mechanics as it's going over this heterogeneity. Okay, so do the same kind of thing, but we take the wind and we point it into the board. So if you remember your Ekman dynamics at all, if we blow the air into the board near the surface, there's going to be an ageostrophic wind to the left. So cool thing here is I'm looking at that's Z, this is distance, that's the streamwise velocity. So if you look at the color bar, these guys here are red, these guys here are negative, they're going that way. These green guys are going this way. So right here, there's where the jump is. You see the secondary circulation pop out. So it appears it's pretty different between whether you have across front winds or along front winds. Okay, just a couple statistics. I got to make sure that the time is good. Okay, so we make statistics, but now we only have one homogeneous direction. So we got to average in Y and time to get statistics. So this is going from warm to warmer. So I picked out this statistic is really good. The gradient in the potential temperature, right where it changes sign, it tracks out where this overshoot is. So here it's turning stable, here it's unstable. So we end up with this non-monotonic behavior that we didn't expect, but shows up real regularly. So if you can imagine if you're floating around outside and you went over a front, where do you measure? Do you measure here, there, there? Anyways, maybe you'd like it over here where it's all transitioned back. The reason for that, it's a super adiabatic layer. What happens is the surface layer responds much more quickly than the outer layers, and you end up with that sort of mechanic. Okay, so one other statistic, if we look at vertical velocity variance, the peak in the vertical velocity variance really matters a lot to people in atmospheric science. W is everything, okay? If you understand W, you understand how the atmosphere works. Well, the peak of the variance isn't way at the back, even though it's warmer there, it's at this intermediate region. So that's a really cool effect. The atmospheric guys, they like vertical fluxes of anything, whether it's momentum or temperature, because those show up in big scale models, not only in LES. So this one's kind of neat. This linear line here is how it started. That's always the basis of simple atmospheric modeling. Okay, but as it goes along at these different positions, you can see how the surface layer responds almost instantly, and it takes a long time for the outer regions of the boundary layer to respond. This black line is this point right here, way downstream. Oh, there's our overshoot right there. So we actually we actually end up with more flux at this point than we do way downstream, and it changes the entrainment. So that's really cool. The other one is warm to cold, so it's the same kind of transition except in the other direction. There's where we start. Surface layer responds immediately. Collapse, collapse, collapse. Okay, so, and it also shows it takes a really long distance downstream to get to equilibrium. Okay, we were talking about secondary circulations, so let's make some more. So this is the case where the geostrophic wind is blowing into the page. This is the vertical velocity, so this is warm, cold, cold. You see the boundary layer collapsing really nice. That's U, so it's the velocity component in that direction, it's negative. Okay, and then here's vertical velocity. That's the instantaneous fields, what they look like. You can see the boundary layer starting to grow right there. If we take those fields and we average like crazy, okay, there it is. This is with a cold front, and you see this nice secondary circulation in the field. Well, it's easy enough to make a warm front. So it spins the other direction. So here's the jump in temperature. So it turns the other way. And so finally, because the ocean's got all kinds of things, there's a filament. Goes here, here. We end up with 2 secondary circulations. So it's really complex, really interesting. Okay. So what physical effect makes the difference between across front winds and a long front wind? So here's just terms in the perturbation momentum budget. So here's the front right here. Okay, so this guy is the vertical flux divergence, d by dz of the turbulent flux. There's the horizontal advection. They primarily balance, and it comes along way downstream there. The key line is this pink one. That's the pressure gradient. Okay, doesn't pop to life. But we look at the other case, okay, now the pressure gradient plays a big role, those same scales on both of them, whereas it didn't here. Okay, so what they're always asking, what's the balance of forces in the momentum equation when you have an SST gradient? Well, what's the difference? Our friend Ekman is the difference. Okay, so we have the same magnitude of geostrophic winds with the long wind case. Okay, it's right here. It's about 8.5 meters per second. But when we turn it around, the component blowing perpendicular to the front is this line. That's about 1.5 meters per second. So horizontal advection dominates with the cross front winds because it's big, whereas barocline pressure gradient wins when the component perpendicular to the isotherms is small. So the atmospheric response depends on how the winds and the SST front are aligned. Okay. Hopefully it's like 4. Oh, okay. Okay, so we talked a lot about SST. Promised to talk about currents. When we started the current exercise, I have to admit, we were like little kids. We should say something about currents. That's what Jim told me. We should say something about currents. Go find it. And so Jim had the very wise idea. He said, let's put an eddy in the box. I said, oh, thank you, Jim. Okay, so what about surface currents in the submesoscale regime? Here's a beautiful picture. This is from Rams. This is the Humboldt current, and it's like art. You can't, I don't know if you could paint a picture that beautiful, but the fluid mechanics does it. So, okay, so here's an LES box. We're going to put an eddy at the bottom. Okay, we're going to have lots and lots of grid points. We wandered around a lot. It ends up that the answer depends on the atmospheric stability. The radius goes from there to there. And what other, oh, we'll talk about how we connect it in just a second. So you can make the eddy rotate this way or that way. That's a neat perturbation on it. Okay, so there's the eddy. This white ring right here is that point right there. It's the maximum velocity. spinning around. So it's solid body rotation. And then Jim had the good idea to damp it in the far field. It looks like that. So that's the eddy we're going to put underneath the LES box. So, of course, it's like all PDEs. If you change the boundary condition, you're going to change the problem. And so we adopted rough wall boundary conditions. Okay, delta U is the difference between the air velocity here and what the water current is there. Okay, that's the momentum flux. That's a standard bulk formula that is routinely used in every atmospheric model. Heat flux is really important, same thing, but notice there's a delta U there and a delta U there. So unsuspecting, they're both the moment, even though we put in a current, we're going to generate a heat flux difference. Okay, and so once we put this in, then the rest of it sprinkles, propagates into the atmosphere. Well, all those red terms show how the surface flux ends up in all the other equations. Okay, so first thing we do, we'll run free convection. Free convection for us means it's just a heated surface. There's no mean winds. There can be turbulent winds, but there's no mean wind. I just wanted to show this box is 37 kilometers with 3,000 points in each direction. This was the first box that Chinho and John did in 1985. That's a 100 cube box, and they studied convection. Here, we have roughly 30 times more grid all over the place. It's the power of supercomputing. Okay, so the interesting thing is here, this is vertical velocity. What the heck is that? This is at 520 meters. What the heck is that? So naturally, you can't let something like that go away. You got to look around. So this is close to the surface where I've zoomed in. Okay, you start to see the Rayleigh-Bernard pattern. Looks fine. A little bit higher up. Oh, here we're about halfway up through the boundary layer. Oh, you see this neat ring. That's vertical velocity coming up. All these dark blue regions are into the or down. Okay, well you have to remember the boundary layer is about 500 meters or so. So that thing is about 10 times the boundary layer height. Okay. So if we go all the way up, there it is. That's the radius of the peak speed of the vortex that we put in the water. Okay, so that eddy in this particular regime is leaving an imprint on the atmosphere at 530 meters. Free convection. Okay. Oh, just a second. Okay. Couldn't resist. You got to look around. Okay. So here we've zoomed in. This is the radial velocity. These yellow ones are flowing out. These blue ones are flowing in. Okay, just to show what it looks like. There it is. So something interesting must happen right here. This is R equals RM, so this is a 4 kilometer radius right there. Okay, there's the tangential speed. And they're going around. It's very beautiful. Nice flow. Okay. Couldn't resist. If you go to an old book, this is a classic solution in Schlichting from 1968. They've taken it out. It's one of the fundamental solutions of Navier-Stokes. It's a laminar flow, but they solved it on this rotating disk. This is what the pattern they get. Down here, okay, the secondary circulation is outward. The disk is spinning like that. Oh, they have a downdraft here in the middle, but it's flowing out. So we've done the convective rotating ABL flow. So in the center, it's like this, the Schlichting solution where it's flow around a rotating disk, but the convection is so powerful, okay, it overwhelms it, and we end up with flow coming in. So it's got both. It's got both. Okay, so really fun. I didn't realize this existed before I did that. Okay, so if we look at the pressure field just downstream, I mean in XY plane, really low pressure. So that secondary circulation looks this way. If we take a cut right through here and plot it, that's what we see. So there's flow outside, goes up, hits the top of the boundary layer, comes down. There's a downdraft right in the middle. Okay, so we end up with this little overturns right here. So it's really funny. So it has a lot of secondary circulations. Okay, just to couple statistics. Those are the momentum fluxes. This is R, distance from the eddy center here. That's the normalized heat flux, temperature flux, excuse me. That's the radial momentum. There's the tangential momentum. Sure enough, there's the statistic VR. It's right near the core. It's positive, it's pushing out. And then outside of that is flowing in. So really nice, really nice. So if we come to, let's say, right here near the top of the boundary layer, sure enough, there's a really neat downdraft right in the center. Okay, now the VR is switched and it's flowing in and then sinks down. Really fun. I want to make sure I end up on time. Okay, so if you take it, that's a cyclonic eddy. If you make it be anticyclonic, sure enough, the momentum flux switches. Okay, now it's negative because it's spinning the other way around. Most of the statistics don't change, but the tangential velocity does. In the cyclonic case, it's going in the same direction that Coriolis wants to turn it. If an anticyclonic eddy, it fights against Coriolis, and that's why you end up with the weak tangential velocity. Okay, just real quick, that's a stagnation ring, makes really big stagnation point there. So the radial turbulent component is really big, okay? And then there's the W variance. It's nearly what the far field value is and goes up. It's got the peak now. Okay. Okay. I want to introduce this quantity because it's not so familiar. We're going to define an anomaly as the magnitude of the wind stress divided by U star squared minus 1. So that's an anomaly. So this is the deviation from that in a normalized unit. Same thing for the scalar flux. Okay, so if we turn on the winds, that was free convection. We turn on the winds, get a different pattern at the bottom. Here's the momentum flux. So we have this big positive anomaly on this side. We end up with a negative anomaly on the lower part. Positive means there's more flux, and there's less flux. So why'd that happen? Pretty apparent. So the winds near the surface are blown across the eddy this way. So all the momentum flux on this side, they're aligned. So it's going to make the currents are aligned with the winds. Over here, they're opposed. So it makes that dipole pattern. So the fun thing then is, does the same thing for the temperature because of the way that they're hooked together. There's a delta U in the bulk formula for tau, a delta U for the scalar flux. So if you stare at it a little bit, this means that there's more, this side is hotter than this side, which is colder, but the winds are blowing sort of this way. So that's like the along front wind case that we had when we had SST variations. So sure enough, you can see it if you take a cut. If you take a cut right through here and you average a little bit, you ask, what's the flow pattern? Okay. So there it is. Okay. So in the pressure, there's a big P, there's a low P. So it wants to drive the air this way, goes up, wants to drive the air that way. Okay. This is the temperature difference. Same kind of thing. It makes a secondary circulation that goes that way. Okay. The imprint is left on the boundary layer because of the buoyancy flux, which is hooked to the momentum flux. I have to remember all those variations were done with constant sea surface temperature when we have the eddy. It's all because of the variations in the tau. Okay, so sure enough, if we rotate the eddy the other way, we end up with secondary circulations switched. That's what it looks like. And then finally, if you look in a YX plane, there's the eddy. Oh, this is done with the fringe calculation, but it hasn't been averaged enough. There's the eddy right there. So it leaves this trailing wake of hot air and cold air right behind it. Really fun. Okay, the winds are blowing that way across it. And then finally, if we go way up to the top, signal's weak, but it's definitely there. Okay, so you can actually see it near the top of the boundary layer. Okay, so there's a vortex. There's a vortex here that spins this way around the box downstream. This is at 7 radii downstream from where the eddy is. Okay, conclusions. All right. I wanted to make sure I didn't go too long. So we showed this sub-mesoscale regime is real interesting. It has all this really interesting dynamics around it. Okay, horizontal scales, 100 meters, 10 kilometers, makes this really impressive sort of fluid mechanical soup. We still learned some things with SST fronts. They make secondary circulations. They modify the fluxes in really important ways. And the response depends on, of course, outside you end up with all kinds of configurations. You end up with the wind oriented at all kinds of different angles to the SST front, and that matters. So the eddy currents, we should have had foresight to say that was going to happen. But an eddy current induces both mechanical and thermodynamical heterogeneity in the pattern. So we end up with the dipole pattern in fluxes, even with constant SST. So it depends on the stratification. If the convection is really strong, the winds are really light, you can see this really beautiful pattern at the top of the boundary layer. As the winds pick up in speed, convection dies down, gets more and more compressed to the surface. Okay, so thing is, we didn't do nature, but measurement people always ask me, tell me what to measure. Give me some clues. Give me a hint. Give me a hint, because the ocean is so big. Give me a hint to look at for something that might be interesting. So that's what these are. It's a hint. Okay. If you went to a place in the ocean where they had a really neat eddy, okay, it would be worth spending time to look at surface layer measurements, etc. So we posed this bold question, probably too scary. Are there teleconnections? That's the climate term. Okay, between remote connections between two different processes. Are there teleconnections between when the ocean does that and clouds? Okay, that's from a climate perspective, that's what you'd really like to know. So how does this, and this, are they connected in a really cool way? I'll stop there. Thanks. I scared everybody.
Especially the last figure.
Yeah, very nice. Thank you. So in your simulation, the ocean eddy is fixed.
Yep, it's just.
If you let it go, it would move, right?
Oh yes. Oh yes.
Okay.
Yeah.
So that will be a couple ocean, right?
Yeah. So one of the things, like I said, Jim had a good idea, because if you put it in eddy, it's then independent of the wind direction. So that immediately eliminates a whole bunch of hunting around in the parameter space to what it's. The other one was just too complicated, but of course you can make the eddy move with the net current, etc. You know. Yep.
Okay.
Yep. And so I'm quite sure other things would happen.
All right. Thank you.
Thanks, Peter. So you showed some satellite images of harmful algal blooms over the ocean.
Yep.
I was wondering, it's like, can it be like a PIV over larger scale if you have multiple measurements of satellite, can we estimate velocity fields?
It's if you go to that image,
Yes.
there's a whole bunch of images similar to this stored someplace on that web page. I'm quite sure you could think of those as mainstream lines,
Mhm.
you know, and if you zoomed in enough, maybe they're particles, but it's actually frightening to think about the complexity of what that's actually doing.
Mm.
But that kind of happens routinely when you zoom down. It ends up that the people making satellite measurement, can they squish the resolution down enough so that you can actually see things
Mhm.
like that? You know, better microscope. Yeah.
Thank you.
Anyway, so yeah, I have a question that is from the front and from the filament and also the eddies. And so I see this heterogeneity thing makes this MO similarity violated
Oh, of course.
big time.
Of course.
So what's your comments on those who use MO similarity in those methods?
Well, it was
models?
interesting. We were talking with Michael about how LAS boundary conditions are imposed. And I said, that's really one of the sore points of all LES modeling with rough walls. Nobody wants to work on that problem because it doesn't seem real catchy or fun, but that's really what you want to work on is the marriage of those two things, taking a measurement and trying to connect it to how the observational guys in LES actually use that information. So of course, MO assumes all this heterogeneity, it doesn't count, doesn't matter, but people do it anyways. That's the point. They do it anyways.
Okay.
Yeah.
Yeah. Well, I
It's a
guess
flaw in outdoor fluid mechanics.
I guess people like Professor Michele would love to hear this, right? From the measurements report. Uh-huh.
Sorry, there's this. I think it was from Parlange and some co-workers. There's this called the pathology of the Molinobuco similarity, which explain all the cases where it doesn't work, and this would be a great example.
Oh yeah, it's one of those. It's a poster child for that. It needs to be made better.
Great.
So, so you're using LES and water.
Oh, okay, this is LES in the air, but we've done lots of LES in the water too.
Oh, okay. That's true. This is LES. You have LES in the air, but we're looking at the water.
That's the ocean surface.
Okay.
What the
all right,
ocean surface looks like. Yeah.
Okay. I'm familiar with Kim and Moen. They say that you need a certain cell size, grid cell size, to actually do LES in water. And that grid cell size is very, very small.
Yep.
How do you do LES on this kind of scale in water? What sort of assumptions are you making? There was a professor here, Professor Song, who used to be here, and he did what he called large LES.
Very large LES.
Very, very large LES. And people would just, they would just poo-poo it. And I thought, well, actually, it makes sense to me.
Yeah.
Very large LES. So is very large LES in vogue now? Can you do that? Or is it still, people are saying you have to go with Kim and Moen?
Okay, so just a couple little points. This problem I did with 10 billion grid points. So it's 81,992 in X. So the delta X is about 1.4 meters. The delta Z starts out, it's about a half a meter, and it's a nice stretch grid. So I've got frontogenesis on top of the Langmuir problem. Okay, that's when you push it. I wanted to push it to where the subgrid scale model was designed to work. Okay, that's in the inertial range of the water. Okay, very large eddy simulation. Okay, really the difference between DNS, very large eddy simulation, all the way down, all the way down, is how you treat the subgrid scale model. Okay, it varies in a very interesting way when you pass from the LES limit to the essentially the RANS limit that the engineering world looks like. So to have very large eddy simulation work, you need a subgrid model that sits in the middle somewhere between LES and RANS. Okay, unfortunately, we don't have that, but in principle, you could do very large eddy simulation if you had the right subgrid scale model sitting in that particular range of motions. Okay, so we talk in the atmospheric literature, there's two terms they use. John Wingard called that terra incognita, the range between RANS and LES, okay? And maybe the spectrum is just barely resolved or partly resolved. It's also a popular term in atmosphere. They call it the gray zone, okay? Especially for clouds. What sort of closure scheme do you need in that gray zone when it's half resolved, half subgrid? Really good.
Thank you.
Hello. Okay. Hi. We have 3 questions from the Zoom
Oh,
that I'll read right now.
okay, cool.
Okay. So the first one is, how do you decide grid size in these simulations?
Just about what I explained right there, and partly learning. Okay, done enough simulations over time. If it's a pedestrian calculation, I know how much. So I push it all the way. So like the air ones were done with 4-meter resolution in the horizontal, maybe 2 meters in Z, something even finer than that. I want it to be really resolved. So it's partly experience, partly knowing the phenomena that you want to work with. Okay, that's how it's done. You can, the other thing is you can run horse simulations. Oh, what's the spectrum do? Where am I at in terms of the spectrum? Do I need more grid? Do I need less grid? You know, that kind of thing.
Thank you. And then the second question that we have is, are these wall model or wall resolved simulations?
No, these are wall modeled. Okay, that's, yep. See, there's an interesting, Philippe Spallart said, there's a thing called QDNS, quasi-DNS. He said, well, the surface layer is viscous, but not too much grid. He calls that QDNS. He says, QDNS isn't worth anything because you need almost the same resolution as regular DNS. So you really want to do one or the other.
Okay. And then our third and final question from the Zoom is, in the transition region, MO similarity might not be valid. What other approach ones can you use in LES if MO similarity is not valid?
We need to figure that out. No, it's a research question.
Well, with that, I think we should conclude the ceremony today. And please join me congratulating Noah for this great honor. Okay, really, okay. And yeah, so I believe, you know, our bioengineering friends will be very happy to see your accomplishment and best wish for your PhD study.
Yep.
And also, well, please join me. Thank Dr. Peter Sullivan for this wonderful talk. By the way, I want to add that, well, Dr. Sullivan was invited and he was just going to come here to give a talk 3 years ago. And then right before his trip, then pandemic happened. And then all those seminars were canceled. Like, yeah. And then, okay, we try to re-invite him back after things loosened up.
Yep.
And then Omega Chrome. So, and finally, we were able to get Dr. Sullivan here. Okay, yeah. So
it was great fun. Invite me back. It's great hearing about fluid mechanics.